Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the final lecture of module 9. In the previous lecture we have been discussing about isotropic moment tensor and CLVD moment tensor. In today's lecture we are going to cover the concept such as the mechanisms for the CLVD moment tensors and its ambiguity, and then we will be having the interpretation of the moment tensor. And finally, we will be seeing the summary of today's lecture. As far as the recap of previous lecture is concerned, we learned that the seismic moment tensor can give the complementary insight into the fault rupture process and can help us in inverting the seismogram in order to estimate source parameters. We assume the equivalent body forces that are similar to the forces that are occurring on an irregular shaped body, and these can produce the same radiation pattern as the slip on an actual fault for the earthquake and the other seismic sources. The seismic sources can be modeled as single forces, force couples and the double couples. So single force, we saw it can be just a single force orienting in any direction. When it is having another force coupled with it, having some offset between them, then it can be called as the force couple. And if you have another force couple that may be having this direction on another direction, then together these will be known as double couples. We saw that the component of the moment tensor represent the fault geometry and the size of the earthquake represented by the scalar moment, that is m naught, that is equal to the product of the shear modulus to the slip of the fault and the area of the fault. Moment tensor, similar to the stress and strain, are symmetric in nature. That means Mij will be equal to Mji, which basically represents that the set of axes for which the off diagonal elements are 0, and it is similar to the stress and strain tensor. Then we learnt about the Green's function, which is basically exhibit the effect of the path when it is coupled with the body force such as the F x naught t naught, then it is used to give the deformation at a point on the surface, that is maybe the displacement. For the moment tensor, if we rotate it into its principal axis, can give the pressure axis, tension axis and the null axis direction. The moment tensor in the array form can be represented by these double couples, and this basically column 1 is represent the offset in x1 direction, this represent the offset in x2 direction, and the column 3 represent the offset in x3 direction. Mij, which is used to denote the component of the moment tensor, where I is the direction of the force couple and J is the offset of the force couple. And the scalar moment, as I told you, is the product of shear modulus, slip on the fault and the area of the fault. And in the component form, it can be represented as this. And in the tensor form, the moment tensor can be written something like this. We also saw that the symmetric property of the moment tensor shows that the slip on either the fault plane or the auxiliary plane yields the same seismic radiation pattern. The trace of the tensor is 0. The scalar moment gives the magnitude of the moment tensor, which is analogous to the magnitude of a vector. Thus, the eigenvectors of the moment tensors are parallel to the tension, pressure and the null axis. The transformation changes the component, but the physical moment of the tensor stays the same. And these two different looking force system in the previous coordinate system and in the rotated coordinate system will give the same radiation pattern of the seismic waves. We also learnt about the isotropic moment tensor, and it has two qualities. All the diagonal terms of the isotropic moment tensors are non-zero and are equal, and which further means that the polarity of the first motion is the same in all the direction, which is similar to the explosion and the implosion. In case we want to have an example of the isotropic moment tensor, then it can be seen something like this, where you can see the diagonal elements are all non-zero and are equal to each other. A moment tensor with a non-zero isotropic component represent a volume change. We also learnt about CLVD, compensated linear vector dipoles, which are a set of three force couples or triple force couple, triple dipole you can say, that are compensated with one dipole is -2 times the magnitude of the other two. So in this example you can see this is the -2 times of the other two. This is your CLVD. And we also talked about the CLVD, and CLVD, as I said, has the one dipole that is of -2 times the magnitude of the other two, and it can be represented in something like this. The other possibilities are this, this, this and this. And these dipoles, compensated linear vector dipoles, are very rare to occur but sometimes observed, usually in the complicated tectonic environment. The trace of the moment tensor, if you look at the sum of the diagonal element, is all 0. So this is not a isotropic component. For CLVDs, two primary explanations were offered. In the first explanation, it was said that in volcanic areas, it is natural to think of an inflating magma dike, which can be modeled as a crack opening under the tension. The moment tensor for such a crack can be represented by this. And if you look at the trace, it is 3 lambda plus 2 mu, and which is positive. That means it represents the crack is opened. We can decompose this particular moment tensor into two terms. So this can be represented by this, that is the summation of this isotropic moment tensor plus a CLVD moment tensor, that is having the one dipole as a -2 times of the other two dipoles. And this is your CLVD and this is your isotropic source. The first term is an isotropic tensor whose diagonal components are E is equal to lambda plus 2 by 3 mu, are 1/3 of the trace, and this is your CLVD. An alternative explanation was also proposed, that is the second explanation for the mechanism of the CLVD. So that CLVD can also be produced due to the simultaneous near earthquakes that are happening nearby the fault of different geometries. So let's suppose there are two faults, one fault, another fault, and there are two earthquakes, and together they can represent the CLVD. So for example, consider the sum of the two dipole sources with moments m0 and 2 m0. So you can see there are two dipole sources, double couple sources. This is the first one and this is the second one. Here it has the moment m0 and this has the 2 m0, and it can be expressed in the principal axis coordinate system, and when we sum them up, then what it will give? It will give the CLVD. So this is coming from the one source of a fault, and this is coming from another nearby fault of another source. Then when together it will be seen as, then these will be represented by this. This may produce a CLVD. So basically what is happening, the two faults are there which are nearby, and simultaneously two earthquakes has happened onto both of the fault, and together it will be observed in the moment tensor as CLVD like this. Thus adding these two dipole couples yields a CLVD. So when you decomposing a CLVD into double couple bears out the concept that the moment tensor can be decomposed in different ways. with different interpretations. This is because the moment tensor represents the equivalent body force system. So different decompositions reflect the same force system and give the same seismic waves. Hence, the seismic waves alone cannot distinguish between the alternative decompositions. The multiple faulting events give rise to apparent CLVDs have been reported. So in this case, you can see that there is an example of CLVD type focal mechanism for caldera earthquake, and you can see there is this volcanic eruption is happening, magma is rising up along the conduit, and then the plug may go down like this, and this may represent the CLVD. In general, once a moment tensor has been found by inverting seismogram, it will be more complicated than expecting a double couple. Even if the source were a pure double couple, the noise in the data and imperfect knowledge of the earth structure would likely produce a tensor that once diagonalized would look like this, where lambda 1 is greater than lambda 2 is greater than lambda 3, the modulus of these. And if this double couple represents a moment tensor, then lambda 1 will be equal to minus lambda 2 and lambda 3 will be 0. And in most cases what happens, lambda 1 is nearly equal to minus lambda 2, it is not exactly equal to lambda 2, and modulus of lambda 2 is far greater than the lambda 3. So M is approximate but not exactly a double couple. In this case, we want to interpret the moment tensor by decomposing it as we did in the case of CLVD, and for that purpose we are going to see that the inversion of the moment tensors for shallow earthquake cannot resolve the isotropic component. We remove it via this. So lambda 1, lambda 2, lambda 3, this is the moment tensor, and we can decompose it into its isotropic component and another moment tensor, that is lambda dash, lambda 2 dash and lambda 3 dash, which is basically a deviatoric moment tensor, and E is basically the lambda 1 plus lambda 2 plus lambda 3 by 3, that is the mean of the diagonal element of the moment tensor. And the value of lambda 1 dash will be equal to lambda 1 minus E, value of lambda 2 dash will be equal to lambda 2 minus E, and lambda 3 dash will be equal to lambda 3 minus E. And this deviatoric moment tensor can further be decomposed in several ways, and one of the way to decompose it into its major and minor double couples. And when we decompose it, it will look something like this. This is your major double couple and this is your minor double couple. And the first tensor is the major double couple with scalar moment lambda 1 dash, and the second minor double couple with scalar moment lambda 3 dash. And the major double couple is generally much larger than the minor double couple, so we treat the major double couple as the earthquake's source mechanism. This is an example which is taken from Stein and the Weissschen book. An intermediate depth thrust earthquake in Kuril subduction zone near Japan. Components are in the unit of 10 to the power 27 dyne centimeter. The moment tensor looks something like this for this earthquake originally. When we are going to diagonalizing this particular moment tensor in the principal coordinate system, then it may look something like this. And when we will decompose it into its component, major and the minor component, then it may look something like this. And the unit vectors or the eigenvectors n1 cap, n2 cap and n3 cap may be something like this. And the n1 cap is basically representing the pressure axis of the double couple, and n2 cap representing the T axis or the tension axis, and the n3 cap is representing the null axis. The isotropic component was constrained in the inversion to be 0. Because the minor couple has a moment of only 6%, that means this is very smaller than this one, and this is your major couple. So we assume that the major couple represents the earthquake mechanism, as we have said in the previous slide, these convert into the thrust on a fault plane striking in north 180 degree east and dipping in the 23 degree west. You can also decompose the moment tensor in many other ways, and one way is to decompose it into its double couple and a CLVD. So you can decompose this moment tensor into these moment tensor, and these moment tensor, you can see this one is the CLVD and this is a double couple. So generally the rule is the moment tensor for CLVD will look something like this. You can take the third element, do the half of it, take the negative of it. Again you can do the same thing for the M22 component, and for M33 you can take the same lambda 3 dash as it is, and for the other double couple, this one double couple, you can calculate using these expressions. And the relative strength we talk about of a double couple, the CLVD is given by the ratio of the smallest and the largest deviatoric eigenvalues, that is epsilon, that is equal to lambda 3 dash by lambda 1 dash. And epsilon, if it is 0, indicates a pure double couple. If it is plus minus 0.5, that indicates a pure CLVD source. About 4% of the mechanisms in the Harvard Global CMT Tensor Catalog, that is a catalog that you can download for a specific time period and for a specific area from the Harvard Global Moment Tensor Catalog, that is derived from basically the waveform inversions that are not constrained to yield double couples and have epsilon modulus greater than equal to 0.3. And some of these artifacts may be of the inversion process similar to the spurious minor double couples, and some appear to be the real source effect. And the decomposition, as I said, can be done in many ways. So decompositions are always non-unique, and it can be decomposed like this, and also it can be decomposed like this. So that means decompositions are non-unique in nature. As far as the summary of the module is concerned, we previously learned about the elastic rebound theory, which was first given by H. Reed after the occurrence of the famous California earthquake in 1906. And then elastic rebound theory was divided into the 4 stages and the phases. The first one is the interseismic stage, second one is the pre-seismic stage, third is the co-seismic phase, fourth is the post-seismic phase. And as per the elastic rebound theory, the strain accumulated around the rock, and when it gets above, then the rock can withstand, then it generates a slip in the form of an earthquake. The interseismic stage makes the most of the seismic cycle, and it consists of the long period between 2 large earthquakes during which elastic strain accumulation occurs in the broad region. Pre-seismic stage consists of the foreshocks or the small earthquakes, and the co-seismic phase is the earthquake itself, where the rapid motion on the fault occurs and that generates the seismic wave. Post-seismic phase occurs after the earthquake, that is the phase when the aftershocks happens, and the transient afterslip occur for a period of years. There are the 2 coordinate systems we talked about, phi delta lambda and n cap d cap, that is for the unit normal vector on the fault plane. D cap is the slip vector along the slip direction. Normal vector to the fault plane can be represented by this, and the slip vector, a unit vector in the slip direction, can be represented by this. And pure strike slip fault are of 2 types, the left lateral and the right lateral strike slip fault. In case of the hanging block is moving to the right, the motion is left lateral. In that case, the lambda will be equal to 0, that is the slip angle, and lambda is 180 degree in the case of right lateral strike slip fault. Dip slip fault are of 2 types, one is normal, another is the thrust fault or the reverse fault. For the reverse fault, the slip angle is 90 degree, and for the normal fault, the slip angle is 270 degree. Then we talked about the focal mechanism, and we saw that the seismogram recorded at various distances and azimuth can be used to study the geometry of the faulting. Those are known as focal mechanism. And it uses the fact that the patterns of radiated seismic waves depend on the fault geometry. And then we talked about the first motion, and there are the two deformations. One is the compressional, another one is the dilatational, and the zone of deformation can be divided into the four quadrants, two for the compressional and the two for the dilatational. And these quadrants are separated by fault plane and the auxiliary plane. The elastic radiations can be described as resulting from double couple of the forces, and these forces are known as equivalent body forces for the fault slip. The radiation pattern for the P wave and S wave can be represented by this expression and this expression. The amplitude in the radial direction can be written as 1 by 4 pi rho alpha cube r, that is inversely proportional to the distance. And there is this seismic movement rate function, and this is the radiation pattern sin 2 theta cos phi. And for the shear wave, it has u theta and u phi, and there is this amplitude term. This is the seismic movement rate function, and this is your radiation pattern. Similarly, for u phi, it is there. We then learnt about the seismic movement tensor, which can be used to give additional insight into the rupture process and can be used to estimate the source parameters. We assume that the equivalent body forces can be used to represent the overall forces, actual forces that are acting on the fault plane, and this will represent the same radiation pattern as that of the faulting that is actually happening onto the fault, and also the other seismic sources. The seismic sources also can be modeled using the single force, force couple and the double couple, and the single force can be something like this. In the case of the force couple, there will be another force which will be offset by a distance, and there will be a force double couple which can also be having another force couple, and together this will be known as the double couple. In case the component of the moment tensor that is representing the fault geometry, the size of the earthquake can be represented by the scalar moment, that is m naught, that is equal to the product of the shear modulus and the slip and the area on the fault. The moment tensor is symmetric in nature. This is the property similar to the stress and strain tensor, and we can always find a set of axes which will make off diagonal elements 0, and which we have done in the case of the continuum mechanics for the earthquakes when we talked about the seismic waves for the stress and strain. Then we talked about the Green's function that relates to the path effect of the seismic waves when it is coupled with the body force such as the impulsive force Fx naught T naught, for example delta function, then it may represent the deformation happening at a point on the surface. That means, for example, the displacement. The moment tensor can be rotated into its principal axis such as the pressure axis, tension axis and the null directions. Moment tensor can be represented by this array of the 9 double couples. The first column is representing the forces having the offset in the x1 direction. Second column is representing the double couples for which the offset are happening in the x2 direction. And third column is representing the double couples where the offset is happening into the x3 direction. Mij in the subscript ij, where I is the direction of the force couple, j is the offset of the force couple, and the scalar moment m naught is the product of the shear modulus, slip and the area on the fault. It can also be represented by this expression, and in the tensor form it can be represented by this particular matrix. Then we talked about the properties of the moment tensor. The moment tensor are symmetric in nature. That shows that the slip either happening on the fault plane or maybe the auxiliary plane will always give you the same seismic radiation pattern. The trace of the moment tensor, that is basically the sum of the diagonal components, will always be 0. The scalar moment can be represented by this particular expression, which is analogous to the magnitude of a vector. And then we saw that the eigenvectors of the moment tensors are parallel to the pressure, tension and the null axis direction. The transformation, if we do, something similar to the rotation of the moment tensor, then the physical movement of the moment tensor will always remain same. That means if you are having the previous coordinate system and the transformative coordinate system, the force or the radiation pattern of the seismic wave will always be same. Then we talked about isotropic moment tensor, where the diagonal elements are non-zero and all are equal. And in this case, the polarity of the first motion will be same in all the directions. The moment tensor is non-zero for the isotropic component. That means the volume change is happening. That is similar to the explosion and the implosion. In the case of explosion, the double couples are all positive. In the case of implosion, the double couples are all negative. Then we talk about CLVDs. The expanded form of it is compensated linear vector dipoles. This is basically a triple dipole and are compensated, where the one dipole is negative 2 times of the magnitude of the others. So if you look at this one, then this one is the negative 2 times of the other two. Those are in the x2 and the x3 direction. The one way of describing the CLVDs, or you can say the mechanism of the CLVDs, can be described in two ways. One is for the volcanic areas where the magma is inflating in the form of dike and can be modeled as a crack opening under tension. So this can be modeled as something like this. And alternative explanation is that if suppose there are two faults, those are nearby and simultaneously two earthquakes are happening, then it can be represented by CLVD. Multiple faulting events can also give rise to the apparent CLVDs, have been reported by many authors and the scientists. And the deviatoric moment tensor can be decomposed in several ways. One is having the major couple and another one is having the minor double couple. So let's suppose this is your deviatoric moment tensor. It can be represented into its major double couple and into its minor double couple. And this is all about the module 9, where we learnt about the moment tensors, first motions, and also the geometry of the faults. In the next lecture, we will have the brief on the geodesy, earthquake geodesy, and these are the references of today's lecture. This is all. Thank you so much. Bye-bye.